Welcome to The Explainer. Today we're on the trail of a mystery. It's an energy heist that happens constantly, all over the world, in every ecosystem. And we're going to follow the clues to figure out exactly where all that energy goes. So let's kick things off with a question that gets right to the point. I mean, think about it. Why are there so many plants, a good number of gazelles, but way, way fewer lions? It seems like it's just about who eats who, but the real reason is all about energy. To crack this case, we have to think like detectives. In our first move, we've got to follow the energy. Right, so we've all seen that classic food chain diagram in school. You know, the sun gives energy to the plants, a rabbit eats the plants, and a fox eats the rabbit. Looks simple, right? But the real story, the part that's actually fascinating, is how much energy really makes it from one link in that chain to the next. Okay, so let's zoom in on our first crime scene. We're going to watch this energy heist happen in real time by focusing on just one single meal, a caterpillar having a nice lunch on a leaf. Let's just say, for the sake of easy math, that this leaf contains exactly 100 kilocalories of energy. You can think of that like a $100 bill. The caterpillar just swallowed 100 units of pure energy currency. Now, you'd think that whatever eats the caterpillar gets that full 100 kilocalories, right? But nope, this is where our great energy heist really gets going. Most of that energy seems to just vanish. So where did that $100 bill go? Well, get this. A massive 50 kilocalories, that's half of the energy, is lost right away as waste. Another 35 kilocalories get burned up just to keep the caterpillar running. You know, moving, breathing, just being a caterpillar. That whole process is called respiration. So here's the punchline. After all is said and done, only 15 of those original 100 kilocalories actually get stored in the caterpillar's body as new tissue, as growth. And that's the only energy available for the bird that comes along and eats it. A crazy 85% of the original energy is just gone from the food chain. Okay, so we know a huge amount of energy gets lost. But why exactly? Let's lay out the main culprits responsible for this giant energy escape that's happening everywhere. It all breaks down into about 5 key stages. First, not everything gets eaten. Then, not everything that is eaten can be digested. Then, the energy that does get absorbed is used for staying alive, breathing, moving. And all along the way, energy is constantly leaking out as body heat. It's like a super leaky pipeline at every single step. And that first point is a huge one. Incomplete consumption. I mean, when a lion takes down a zebra, it doesn't eat the bones, the hooves, or the fur. All the energy that's locked up in those parts, it's lost to the lion. It goes to the decomposers instead. So now that we know why the energy gets lost, let's look at a really simple rule that helps us figure out how much gets lost. This is a really fundamental idea in all of ecology. Scientists, of course, have a term for this: ecological efficiency. It's basically just a measure of what percentage of energy gets passed on from one level of the food chain, what they call a trophic level, to the very next one. So from plants to herbivores, and then from herbivores to carnivores. And here's the super useful rule of thumb you need to remember. Only about 10% of the energy makes it from one level to the next. So for every 1,000 calories of grass out there, a cow that eats it might only store about 100 of those calories in its body. This is exactly why you have that classic pyramid shape. There's just less and less energy to go around the higher up you get. All right, it's time to put on our detective hats. Let's take what we've learned and apply it to a scenario and see if we can solve the case ourselves. Here's our case file. In this particular ecosystem, the producers, that's our plants, they capture 21,000 units of energy from the sun. The primary consumers, the critters that eat those plants, they only manage to get 3,330 of those units. So here's your mission, detective. Based on those two numbers, what was the exact ecological efficiency? How good was this ecosystem at passing energy from that first level up to the second? And here's the simple formula we need to crack the case. You just take the energy that made it to the next level, divide it by the total energy that was available to begin with, and then multiply by 100 to get your percentage. Okay, let's plug in our numbers. We've got 3,330 units that were passed on, and we'll divide that by the 21,000 units that the plants started with. And there's our answer, 15.7%. This is actually a perfect example of how that 10% rule is a great guideline, but it's not a strict law. Real life varies, and this particular ecosystem was actually a little more efficient than average.
So let's do a quick wrap-up of our energy heist investigation. The big takeaway is that a ton of energy is lost at every single step of a food chain. We know it's because of things like waste and just the energy it takes to live. We can measure this transfer using something called ecological efficiency, and that 10% rule is a fantastic shortcut for understanding why there are always fewer predators than prey.
And that leaves us with one final and really important question to think about. If we know that as much as 90% of energy is lost every time we move up a step in the food chain, what does this basic law of nature mean for us, for trying to feed a growing human population on a planet that only has so many resources? The answer to that? Well, that's something worth chewing on.